So for today's presentation, I will be doing a presentation on MO diagrams of three different molecules. So we'll see here we have dinitrogen here, carbon monoxide, and O2 2+, and they all have triple bonds according to their MO theory, but they have significant differences. So in this presentation, I will show the different MO diagrams and show that they all have triple bonds to the MO theory and show the differences and similarities between each of these molecules. Okay, first up we have dinitrogen. So you'll have there, and we have the electronic configuration. You have 2s2, 2p3 configuration here on an MO diagram. So let's pull it up. Here it is. We have nitrogen here and nitrogen here. And I have the 2p here and the 2p here, and then the MO diagram here. So each nitrogen have a total of 5 electrons. So here, 2s2 here. So we'll have a total of 10 electrons for this MO diagram. So let's plug it in. Configuration. And so here are all the electrons. So we'll have 1, 2, 3, 4, 5 here, there, and then 5 again here. So we'll plug them all in, as you see, using the Aufbau principle and Hund's rule to plug them in. And you see here, you can use this to calculate the bond order here. So you have 1, 2, 3, 4, 5, 6, 7, 8 bonds in electrons, and you have 2 here that are anti-bonding electrons. So A minus 2 divided by 2 equals 3. And this 3 here shows that the dinitrogen has a stable triple bond. And if you were to draw the Lewis structure of dinitrogen, you'd be able to see the stable bond. So we will get up here, and as you can see here, the triple bond here shown from the bond order and the whole MO diagram here. So next molecule we have is carbon monoxide. So you can see CO here. So the electronic configuration for carbon 2s2, 2p2, and then for oxygen 2s2, 2p4. So let's pull up an MO diagram. So right off the bat, you can see the differences from nitrogen, obviously different atoms, but because they are two different atoms, they will have different energies. So the orbitals here have different energies to each other, so that affects how we draw the diagram. I see the carbon has higher energies than the oxygen. So then let's plug them in. So you can see here the 2s2, 2s2 there, 2p2, 2p2 there, oxygen 2s2, 2s2 there, similarly, obviously on different energies, and then the 2p4, 2p4 there again, energies. So put them in using the Aufbau principle and Hund's rule. And so that obviously the main differences between this and nitrogen are the energy levels of the two different atoms. But the similarities between the two of them are their bond order. So the bond order here is 3, calculating it with the 2, 3, 4, 5, 6, 7, 8 bonds in minus the 2. Antibonding divided by 2, you get 3. And then that shows the triple bond. And you show up the Lewis structure of it. And again, there you can see the stable triple bond showed from the bond order, showed from the whole diagram, which is very similar looking to the dinitrogen Lewis structure. Again, another similarity. And now we are on to our final molecule here of O2 2+. So the electronic configuration of that will be 2s2, 2p2 instead of 2p4, and that's obviously due to the lot of electrons here. It shows the 2+. So let's draw an MO diagram for, there's the oxygen there, obviously similar to the N2, same energies because they're the same atom, but different to the dinitrogen. As you can see here, the 3 sigma G is attracted a little more to the nucleus than the pi, so they switch places. Because obviously from the dinitrogen, sigma G here was up here, and the 1 pi were lower, and now they've switched due to the sigma G being a little more closely attracted to the nucleus. So let's plug in the. So you can see here 2p3 here, 2p3 here, because obviously electron lost on each to show the 2 plus. And again, use the alpha principle rule. So you'll have 2s2 plug them in here, and the 2p3 plug them in here. And again, very similar to the nitrogen, is the bond order 8 minus 2 divided by 2, which equals 3. And again, shows the triple bond within the species, but obviously the difference, significant difference, is the 3 sigma G having a lot closer to the nucleus, being more attracted to it, so these places. And now finally, our little side question is how would removing electrons from O2 to make O2 2 plus increase the bond order for O2 plus? So we get up O2, you can see 2s2 and 2p fall. Obviously O2 2 plus 2p 2. So we have 2 extra electrons on the 2p. And with these 2 extra electrons being added, we have 2 electrons in the anti-bonding. So 1 there and 1 there. So this will change the bond order because, to get the bond order up, it would be 8 minus 4 instead of 8 minus 2. The bond order of 2. So obviously removing these 2 electrons would remove the 2 anti-bonding electrons. That would make it 8 minus 2, and then they'll increase that bond order to 3 instead of 2. So that is how removing the electrons would increase the bond order. Thank you so much for listening to my presentation.